Good evening, students. Very interesting topic today is the topic of resistance of a network. Now, in class 10th and 12th, you do a certain type of network. When I say network, this is basically a lot of resistance connected in series and parallel, and you have to find, the equivalent resistance of the network. Now, these questions where you're supposed to find the equivalent resistance, typically are series in parallel, and there is some analytical step that helps you identify that what is in series and what is in parallel. So you can see my YouTube videos that explain how to identify a series circuit and how to identify a parallel circuit. Now, today I will not talk about the equivalent resistance of a finite network. So what you've been doing in class 10th and 12th, maybe the more focus is on finite networks. Now, finite networks, okay, the word is finite networks. See, these are having a fixed number of resistors. So I can draw a circuit and say, this is my finite network, and this is my, so what I'm drawing and giving you is an example of a finite network. So let's draw a finite network, and okay, and maybe you have one more, and maybe one more here, and and this. So I've done some solutions on how do you solve the finite networks. You can go to my YouTube channel and search for how do you solve finite networks. They have limited number of resistors. So you have R1, you have R2, and R3, R4, and then you have R5, R6, R7, and R8. Okay, and maybe you're supposed to find the equivalent resistance across these 2 points. Okay, these 2 points are A and B, and then you can decide these two are in series, and then the combination of R7 and R8 is in parallel with R6, and then you can continue so on and so forth. And you might get struck at some places within finite network. There are techniques how to solve those types of problems. But today what I'm going to talk about is the concept of the infinite series, okay? Infinite series. Now, infinite series is basically a bit intricate and bit complicated and takes the complexity of networks to a different level altogether. Now, this is what a infinite series looks like. Okay, so I'm just going to draw an infinite series. We are going to today solve this problem, not this problem. I think these are relatively simple, but they have their own complexity. These are very different type of networks, and you can see one example. Very important if you're preparing for JEE Mains and JEE Advanced, and sometimes these questions can be asked in NEET. Very unlikely because these are a bit mathematical, but if you know about this level of complexity is good to know, but more focus is on JEE Mains and JEE Advanced. Okay, so what you do is you draw a network, and so I will draw a very simple one. We can do add further layers of complexity in this, but we will do something simple today. So this is your 1 ohm, this is your 1 ohm, and this is your 1 ohm, and I repeat this pattern continuously. Okay, and so you can see I'm drawing 1 1 1 1 ohm, 1 ohm, and 1 ohm, and then this is 1 1 1, and this is 1 1 1. Okay, and then this continues till infinity, which means it's an infinite network. So this network never comes to end and continues till infinity. And you are supposed to find the resistance between the points A and B. These are the 2 points you're supposed to find the equivalent resistance. Like you had to find the equivalent resistance here, you're just supposed to find the equivalent resistance between A and B for an infinite network. Now, infinite networks are different in their approach and strategy, and this is how it works out. See, since now we are talking about solution now and what should be our strategy. There are multiple ways you can solve these questions, but we will pick up which is least mathematical and easiest to understand. Okay. Now, since the network is infinite, if you say that the resistance here is R, okay, between A and B, this is your R, total resistance. Then, if you take something out of something which is infinite, the answer does not change, right? It still remains infinite. So if you pick a chunk of some stuff out of some infinite thing, the stuff still remains infinite. Similarly, if you remove one repeating pattern, now what is repeating pattern? You can see this is A, this is B, and this is C. This is again A, this is again B, and this is again C. This is A, this is B, and this is C. And this is A, this is B, and C. So you can see the repeating pattern is A, B, C. And so when you do more complicated, infinite network problems, the first step you have to do is to identify the repeating pattern. Now, since this is an infinitely repeating pattern, remove one of the one of them, which is maybe 1 A, B, C. The answer will not change. So if you think like this, what is happening is you draw one pattern, which is here, 1, 1, 1, and then the pattern repeats at this point. Okay, the pattern is repeating after this point. So this is your 1, and this is your, and now the rest of the network, which starts from this point, also has an equivalent resistance of R between these 2 points. Okay, between these 2 points, because if you remove one small part of that infinite ladder, this is mainly called as a ladder. Okay, so nothing is going to happen, and you will still get an R here. Okay, because from this point onwards, you're again infinity, and therefore these 2 points, the resistance you get is same as what you get here between the points A and B. What you've done is you have removed a small part of the ladder and kept rest of the ladder as infinity. So even if you remove and cut off one part of the ladder, the rest of the part still remains infinite. And the resistance here has been assumed to be R. Now, if you see carefully, this is 1, this is 1, this is 1. These two are in parallel, and therefore the answer is R into 1 upon R plus 1. Okay? So I can redraw this circuit and substitute these two as 1 ohm and one common resistance, which is R into 1 upon R plus 1, and this is 1, 1, and this is R. Okay, equivalent. So this is the way the pattern emerges, and now you can see that R equivalent, which is this, is made up of 3 resistors, A, second, and third. Okay, so 1 plus R into 1 upon R plus 1 plus 1. So this actually becomes R is equal to 2 plus R into 1 upon R plus 1. And if you take the LCM of these two, what you get is, R into R plus 1 is equal to 2 R plus 1 plus R, and this is your R square plus R is equal to 2R plus 2 plus R, and this is r gets cancelled here, and what you're left with is r square is equal to 2 plus r, and this is r square minus r minus 2 is equal to 0. And if you solve this quadratic, which is r square minus r minus 2, you get r is equal to 1 plus minus 1 plus 8 divided by 2 is equal to 1 plus, ignore the negative sign in the quadratic because you can't have a negative resistance. So r is equal to under root of 9 divided by 2 is equal to 1 plus 3 by 2 is equal to 2 ohms. This is the way you need to solve an infinite ladder problem, right? So finite networks are complex, sometimes difficult to solve, but infinite ladders actually are very different in their strategy. And most of the easiest way to do was this. There are many other ways you can solve an infinite series using some mathematical techniques and the knowledge of series and parallel. But they're way too complicated for this examination. But if you have understood this should be sufficient for your knowledge. So convert all of this into a quadratic equation finally. And that's how you solve an infinite ladder network problem for equivalent resistance. I conduct live classes and I teach students physics, very concept-oriented physics for NEET, JEE students, aspirants. If you're a hardworking student, inspired to build career, contact me, send me a WhatsApp message, and you're most welcome to join my live classes. I also have 1,500 videos on a YouTube channel, which I've been gradually building. And you can find a lot of concepts and numericals already solved there. But nothing beats a live class and interactive discussion and concept discussion that really ensures that the concept is ingrained in your mind. So I look forward to see you and talk to you. Please send me your valuable comments and feedback on what are the topics you would like me to cover. Thank you very much and have a great day. Thank you.